You know, in computer science, there are some problems that are just impossible. I don't mean hard, I mean mathematically proven to be unsolvable. And for almost 100 years, one problem has been the big one, the final boss. But what if? What if that's not the end of the story?
So in this explainer, we're going to dive into a wild new theory that claims it can do the impossible. We're not talking about chipping away at the edges here. This thing claims to solve the whole problem by basically throwing out the old rulebook. So yeah, let's break down how it even thinks it can pull this off.
All right, first things first, we got to meet the reigning undefeated champion of computational limits, the one, the only, halting problem.
Okay, so the question itself sounds pretty simple, right? Can you write one program that can look at any other program and tell you for sure, yep, this one will eventually stop, or nope, this one's going to run forever? The thing is, the legendary Alan Turing didn't just say, that's tough, he mathematically proved it's impossible. This isn't just a tech hurdle we haven't cleared yet, it's treated like a fundamental law of the universe, like gravity for computers.
But, and this is the crucial detail, Turing's proof, as solid as it is, has a very specific set of rules. It only applies to what we call a Turing machine. And what's that? Well, it's basically every computer you've ever used. It's a computer that does things one step at a time, sequentially. It's the world we're all living in.
I mean, his paper from 1936 is one of the absolute cornerstones of computer science. It literally gave us the concept of what a computer can and can't do. And for nearly a century, the halting problem has been that big, flashing, do not cross sign at the edge of computation.
But now, a brand new challenger is stepping into the ring, and it's claiming that do not cross sign, well, maybe it's not so permanent after all.
This new idea is called the field theoretic solution, and its whole game plan? It's to completely refuse to fight by the old rules. It's not just a new move, it's a whole different sport.
And this is where it gets really interesting. Think about it like this. A regular Turing machine is like you trying to solve a maze by actually walking through it, right? You can only see the path right in front of you. But this field system, it's like floating above the maze and seeing the whole thing at once. It's not taking steps, it's just observing the entire system from the outside.
And this is the face of our challenger, the sovereign field equation. And look, don't worry, there's not going to be a pop quiz. The key thing to get here is just how different this is. It's a system of 9 parts all working together to create this massive field that represents every single possible computer program all at the same time.
So you're probably wondering, how on earth does a big math equation solve anything? Well, let's get into the challenger's secret weapon, this incredible ability to see everything all at once.
It basically boils down to a 3-step process. First up, encode. Imagine every computer program that could possibly exist is plotted onto a giant map, each one with its own unique address. Next, observe. Now, instead of running just one program, the system just watches the entire map simultaneously. It's looking for which points on the map settle down and become stable. And finally, decide. The points that become stable, those are the programs that halt. The ones that keep wiggling around and changing, those are the ones that run forever. So the answer isn't calculated, it's just an observable property of the whole system.
And to do that observing part, the system is tracking 5 key things across that entire field.
Yeah, you can really think of these like a doctor checking a patient's vital signs. The system is looking for signs of stability. Is the energy of the program settling down? Is its memory usage evening out? Is all the background noise fading? Once all 5 of these vital signs flatline for a point on that map, bang! The system knows its answer. That program halts.
Okay, and this brings us to the main event, the million-dollar question. How does this completely new approach dodge the legendary knockout punch, the paradox that has defeated every other challenger for almost a century?
So, Turing's original proof is built on this absolutely brilliant logical trap. Just imagine a mischievous little program, a liar program. It asks the halting problem solver, hey, are you about to tell me that I'm going to halt? If the solver says, yes, you're going to halt, the liar program just goes, nope, and immediately jumps into an infinite loop. But if the solver says, no, you're going to run forever, the liar program just stops right there. See the problem? No matter what the solver says, it's wrong. It's a perfect paradox that proves a step-by-step solver can't exist.
But, and this is the incredible claim, according to the analysis of this new field theoretic system, that whole trap is just irrelevant. The source paper is really blunt about it. It says the core argument, the one that the whole unsolvable proof is built on, simply does not apply. Wow.
So why doesn't the trap work? Well, it's because there's no step-by-step process for the liar program to trick. The system is watching everything at the same time. There's no back and forth, no moment where the liar program can ask its tricky question and then do the opposite. That paradoxical program, it's just another little dot on the giant map, and its behavior is just part of the overall picture. The field system isn't calculating an answer, it's seeing it. The answer is a property of the map itself.
So what's the bottom line here? What's the final verdict on our challenger, and more importantly, what on earth does it mean if this thing is actually right?
Well, the verdict from the analysis is pretty mind-blowing. It concludes that, yeah, the system is mathematically coherent, the logic actually works, and it really, truly does sidestep Turing's paradox. This puts it in a whole new category called a hypercomputer, which is a fancy way of saying it's a theoretical machine that can solve problems a regular computer, a Turing machine, simply cannot.
But of course there's a catch, and it's a pretty huge one. For this whole thing to work, the system needs, well, infinite resources. We're talking infinite parallel channels and the ability to see what happens at the very limit of infinite time. So while it might be a totally valid idea in the world of pure math, it's not something we can, build in the garage tomorrow. It's a mathematical possibility, not an engineering reality. At least, not yet.
But let's just push pause on the engineering problems for a second. Let's get a little wild. What if we could build it? What would that even mean?
Well, for starters, it would completely shatter everything we thought we knew about the limits of computation. It would kick off a brand new era for computer science.
But it goes bigger than that. It could change physics as we know it. I mean, the laws of our universe are all described by field equations. So if those fields can do this kind of hypercomputation, then maybe the universe itself is a computer with more power than we can possibly imagine.
And then there's the biggest question of all. It could force us to totally redefine what it even means to think. If our brains work using physical, field-like processes, well, then maybe our minds aren't just simple computers following a list of instructions.
I mean, think about it. Is that spark of human intuition, that flash of creativity, is it all some form of hypercomputation? Are our own brains solving problems that normal algorithms could never, ever touch? This solution to the halting problem, as theoretical as it is right now, does way more than just challenge a computer science theorem. It challenges our entire understanding of reality, and maybe even consciousness itself.